Hey everyone, welcome to The Explainer. So glad you're here today. We are going to unravel something absolutely crucial, the foundational science behind the very medicines sitting in our cabinets that literally save lives around the world. We're exploring the magnificent, entirely microscopic world of pharmaceutical organic chemistry. I mean, did you know that the exact same chemical element that makes up the graphite in your pencil is the foundation of the life-saving therapeutics you take? It's a topic that might sound a little intimidating at first, but I promise you, once you see how perfectly structured and logical it is, it's going to completely change the way you look at the medical world.
Okay, let's just dive right into this. Think about it. Whether it's a basic painkiller you grab for a headache or an incredibly complex, life-saving treatment, almost every single drug you will ever take is fundamentally constructed from the exact same element, carbon. But why? Out of the entire periodic table, what gives carbon this absolute monopoly over our health and our biology?
Well, to answer that, we've got to talk about organic chemistry itself. And I don't want you to just think of it as some dry branch of science. Think of it more like the language of life. Just like we use a limited set of letters to build words, and those words form complex, meaningful sentences, carbon atoms form the intricate medicinal structures that physically communicate with our biological systems. When you take a medicine, you're essentially sending a molecular message directly to your body, and it's written entirely in carbon. So here is our roadmap for the explainer. We're going to cover the language of life, classifying carbon compounds, chemical bonds and hybridization, electrons and reaction intermediates, organic reaction mechanisms, and finally, we'll wrap up with the foundation of pharmacy. All right, kicking things off with part one, the language of life, building the molecular alphabet. It is honestly wild that one single element acts as the foundational building block for so much. And the secret to carbon's versatility? It's actually beautifully simple. It has this unique ability to form four covalent bonds. Imagine a molecular Lego brick with exactly four connection points. It aggressively bonds with itself to build massive, unbroken chains, or it bends back on itself to form super stable rings. This structural flexibility creates an endless vocabulary of millions of compounds. So a simple gas like methane, a complex ring like benzene, or even everyday medicines like aspirin and paracetamol, they are all just different expressions of that exact same carbon alphabet. Let's move to part two and see how this builds, classifying carbon compounds and organizing those molecules. Now, with millions of potential structures out there, we desperately need a logical way to organize them so we can actually understand how they work. At the highest level, we keep the structural grammar clean by splitting them into two broad categories. First up, acyclic compounds. These are your open, straight, or branch chains, kind of like propane. On the flip side, we have cyclic compounds. This is where the carbon atoms connect to form a closed ring, like benzene or cyclohexane. And honestly, just identifying whether a drug is an open chain or a closed ring tells a pharmaceutical scientist a massive amount about how it's going to behave. Now, what's really interesting about this is the concept of heterocyclic compounds. This is when scientists sneak a guest atom, something totally different like nitrogen or oxygen, right into those carbon rings. Drug makers specifically engineer these heterocyclic rings into medicines because sneaking that non-carbon atom into the structure drastically improves the drug's biological activity. It's like adding a giant exclamation point to the molecular sentence. It makes the drug's effects so much more potent and targeted inside the human body. Okay, part three, chemical bonds and hybridization, the grammar of chemistry. So atoms achieve stability by interacting with each other's electrons, right? And they primarily do this in two ways. With ionic bonds, one atom forcefully snatches an electron from another, creating this really strong, rigid electrostatic attraction with a super high melting point. But then we have covalent bonds, where atoms actively share their electrons. This sharing creates a highly stable, very directional bond. And the key takeaway here? Covalent bonds are absolutely the dominant glue in organic pharmaceutical structures. They provide the stable, precise shapes that drugs need to fit perfectly into your body's receptors. And to really wrap our heads around that 3D shape, we have to look at hybridization, which is basically the mixing of atomic orbitals. When orbitals mix into what's called an sp3 hybrid, they form this 3D pyramid shape called a tetrahedral. An sp2 mix flattens out into a flat triangle, and an sp mix creates a completely straight line. I know it sounds a little abstract, but this invisible geometry completely dictates the physical shape and the actual chemical reactivity of a drug molecule. Which brings us to part four, electrons and reaction intermediates. We're zooming into the kinetic microworld now. Down in this microworld, electrons are incredibly restless. They constantly dance around the molecule. They might permanently pull in one direction, temporarily shift during a reaction, or just completely spread out across the entire structure, which we call resonance. Why does this electron dance matter? Well, it literally dictates whether a drug sits perfectly stable on a pharmacy shelf for years or becomes highly reactive the absolute second it enters her bloodstream. And this brilliantly illustrates what happens while those reactions take place. They form these short-lived puzzle pieces. Take carbocations, these positively charged carbons. They're super social, meaning they are most stable when they're crowded by other carbon groups. But carbanions, the negatively charged ones, they exhibit the exact opposite trend. They prefer to be completely isolated lone wolves. Understanding these fleeting little pieces is exactly how chemists predict the finish line of a reaction.
All right, part 5, organic reaction mechanisms, or how drugs are actually built.
You say, scientists don't just throw chemicals in a beaker and hope they mix. They purposefully construct them using 4 main grammar rules, or mechanisms. They can use addition to attach new atoms across double bonds. They use substitution to precisely swap one atom for another. Elimination strips atoms away to create new bonds. Or they use rearrangement to simply move existing atoms around into a much more stable structure. This is the essential toolkit. It's how chemists actively construct complex modern pharmaceuticals, step by step, entirely from scratch.
Finally, part 6, the foundation of pharmacy. Let's zoom back out.
Let's bring this all together and connect all these crazy microscopic rules directly back to the pharmacy counter. We've explored the alphabet, we've looked at the grammar, but why does this matter to you and me? Because understanding this foundational language is the only way we can effectively synthesize new cures, map out exactly how the human body metabolizes the pill, and rigorously verify the quality of the medicines that save millions of lives every single day. So the crucial point of this entire journey is beautifully captured by chemist Gautam Chandra. He said every drug molecule, every medicinal compound, and every pharmaceutical innovation is based on principles of organic chemistry. Without this invisible scaffolding we've been talking about, modern healthcare simply would not exist. And I'll leave you with this provocative thought to ponder. Now that you understand how we manipulate carbon, the literal language of life, to construct the medicines of today, how do you think the next great breakthrough drug is going to be synthesized tomorrow? The possibilities are quite literally infinite. Thank you so much for joining me on this explainer today. I really hope you feel inspired to keep exploring the incredible world of medicinal chemistry. Keep learning, and I'll catch you in the next one.